So for generating TXY and PXY diagrams, we need to focus on how to generate dew curves and bubble curves. Now the dew curve and the bubble curve are just a collection of points. So this is sort of a recap also of the quiz. So let's focus on the PXY because that's actually the easier one to calculate. So there's a PXY diagram. In this one, the T is some constant value. On the y-axis, we have pressure. On the x-axis, I'm going to call it Z of A, and it'll become more and more clear why I prefer this Z equals A nomenclature. Now, let's try and reconstruct in our heads how a PXY diagram should look. A is always going to be the more volatile component, right? Which means it wants to boil more than component B. So on the quiz, it asked what was the saturation pressure of pure, I think it was hexane, right? That was the more volatile component. So that means 100% hexane is right here on this line. So it should have a higher or lower than decane vapor pressure. Should be higher. So up here, you have the saturation pressure of component A at whatever the system temperature is that this PXY diagram was constructed at. Likewise down here, this is your saturation pressure of component B at the system pressure. Now we're going to be deriving today the equation for these lines. The straight line is the bubble curve, and this curved line is the dew curve. So as we talked about in class on Wednesday, if we want a system to be in equilibrium according to the Gibbs phase rule, we need to lock in two variables. Now, typically, the easiest way to think about this is the temperature and pressure, but that's not always going to be the case, right? You could lock in the composition of one of the two phases and the pressure, and that would still fully define the system. But in this case, if we're locking temperature, which is already constant, and pressure as constant, we would draw a horizontal line. The bubble curve would tell us what the liquid phase composition is. The dew curve would tell us what the vapor phase composition is. Question?
Yeah, and you're showing us how to make this in Excel?
No, we'll drive the equations. You get to discover how to make it in Excel. That's the fun. So, but the key thing to deriving the bubble and dew curves is thinking about what's actually going on in the real process, because that's the critical key aspect. Now, all of this comes down to solving what we call a flash separator. Now, a flash separator, really all it is, like the term flash calculation in thermodynamics, all that it means is you're doing an equilibrium calculation where you're also determining how much of each phase you form. Now, typically for us as chemical engineers, we're dealing with liquid-vapor equilibrium. So in general, a flash drum will be separating liquid and vapor in one equilibrium stage. But the term flash calculation is essentially just saying I have a multi-component, multi-phase mixture. What is the composition of each phase, and what is the amount of each phase? So a crystallization process could be a flash separator. Liquid-liquid extraction, that's a flash separator. But typically for us, we rely on dealing with liquid-vapor equilibrium because, quite frankly, it's the easiest to predict and it's the most commonly encountered type of equilibrium. The reason why it's the easiest is because vapor phases are relatively straightforward to calculate even for non-ideal systems. Liquids are very, very difficult to calculate. So two liquid phases in a flash calculation is extremely hard and requires almost a dedicated thermodynamics class. So you have a feed, which in general, not a hard and fast rule, is typically going to be a liquid because we'd like to transport liquids more so than we'd like to transport gases. Right? Compressors are expensive. Pumps are cheap. Right? Most people, maybe they have an air compressor, right, to fill up tires for their cars or their bikes or something like that. But like a little pond or aquarium tank pump, dirt cheap, right? Pumps for liquids are cheap. Compressors are very expensive. We have a top stream, or oftentimes we'll call it a vapor stream. And we have a bottom stream, or sometimes we'll call it the liquid stream. Somewhat interchangeable nomenclature. Whichever you prefer is totally fine with me. Now, the goal of the flash calculation is we need to figure out all of the mole fractions of every species I and the total amount that comes out of the vapor. Right? For a mass balance, we need to know that. On the liquid side, we want the liquid composition and the total amount of the liquid. Now, generally, we assume that the feed is going to be equal to 1 for a lot of our flash calculations, which means that the top or V or B or L, those are going to be a fractional amount that goes to either the vapor stream or the liquid stream. Reasoning behind this is let's not confuse the mass balance aspect with the thermodynamic aspect. So let's try and simplify it where we first will calculate the thermodynamics and then we'll just rescale our basis for whatever the real process conditions are. It just helps us isolate and organize the calculations a little bit. So generally, the feed is assumed to be 1 for a thermodynamic flash calculation. So, looking at our PXY diagram, what we can do is we can feed a system where the pressure is greater than the bubble pressure for that mixture, right? And then here, we'll say this has some Z of I composition. Now, if we are above the bubble point, let's think about this. We have a fluid at high pressure. It is going to be in the liquid phase. We have a fluid at low pressure. It is going to be in the vapor phase. So if I'm starting off up here, transporting a liquid mixture, and if I want to operate a flash drum, one of the easiest things we'll do will just be to tank the pressure, right? By making the pipe get wider. That'll lower the pressure. So if I'm doing that, I'll be reducing the pressure until I get the very first bubble being formed. That is the bubble point. Conversely, if I start off with an all-vapor mixture and I pressurize it, the first droplet that forms from the liquid phase is the dew point. The key thing here is that the bubble point, this is the first bubble that forms. But how we use this information is critical to how we derive our equations. In this case, the liquid phase composition, X of I, is equal to the total composition of the system. This is the approximation that we rely on to perform our bubble point calculations. Conversely, the dew point, it's the first droplet, and the vapor phase composition is equal to the total composition of the system. So let's take a second and let's think about this. We have the same total composition here. If I'm at a very low pressure, I have no liquid whatsoever. Right? So if I were to grab a volume of that vapor and analyze it, I would exactly get the total composition of the system. As I hit the dew curve, I would draw a line horizontally over here, and this would give me my my liquid phase composition, right? Because I would be at a constant pressure and a constant composition. But at the dew point, it's an infinitesimally small amount of liquid that forms. So little that we don't even really consider it influencing things. So if we were to do a total balance on species I, the total composition times by the feed, which oftentimes we assume is equal to 1, is equal to the vapor mole fraction times by the total amount of vapor plus the liquid mole fraction times by the total amount of liquid. If L is very, 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 very small, right, that means that your Y is going to be equal to your Z. Does that make sense? Conversely, if we're coming from the top down, again, we have exactly the same total composition. Z is the same. If we come down here and we hit the bubble curve, we're going to be forming the very first vapor bubble. But it's such a teeny, teeny, teeny amount in a vast sea of the other fluid, right, that the opposite happens. If your feed, or your total amount, is essentially the same as your liquid, right, that means this term goes away, and that your Z is equal to your X. Your total composition is equal to your liquid composition. Any questions on that?
Sorry, and that's just assuming it's high pressure then?
Yes. So if you take this mixture and you start to pressurize it, first you'll condense one droplet, then you'll condense a lot more, and then eventually you'll have nothing left and you'll be a pure liquid. Now the reason why I highlight this is because the equation for the bubble point and the equation for the dew point are exactly the same thing, right? It is only the assumptions that you make. So let's first start off with a total flash calculation, and then we will simplify it down. So for a two-component flash calculation, right, what we need to discover is yi, so let's say, so y of A, y of B, x of A, x of B, L, and V. Does that make sense? We need to know the composition of the vapor phase, the composition of the liquid phase, the total amount of liquid, and the total amount of vapor, which gives us 6 unknowns. Now let's go through our equations. What are two equations that we're super familiar with after exam 1?
Your mass balance.
Mass balances. How many mass balances do we have? 2 mass balances. Okay? What else do we have? Another thing from the previous exam.
You're going to have a system specification.
In this case here, we're going to assume that we know temperature and pressure. This is our standard flash calculation. We have consistency relationships. Yeah, question?
Would we need to have YB and XB as unknowns when really it's, if that's the fraction and altogether it'd be 1, wouldn't it just be 1 minus YI?
Yes.
YA would be YB.
So we have our two consistency relationships. Yi, summation of Yi's equal 1, and summation of Xi's equal 1. Exactly. Those are the two consistency relationships. Yes?
I thought those, so would those be design specs too? Though?
No, these are just basically equations that have to be true based on the definitions of the mole fraction.
Okay.
It's like 1 + 1 = 2.
And what'd you call those? Sorry.
These are called, in the degrees of freedom sheet, we call these consistency relationships. And we have 2 other equations that we introduced, Raoult's law. All right, and that gives us 0 degrees of freedom. So let's write all these out, and then we'll simplify them down for the bubble curve and the dew curve. This is our flash calculation. So Raoult's law. Well, let's first do our material balance. I'll call it material balance, not mass balance. All right, material balances, you should be able to close your eyes, put your pencil on the paper, and rattle off the material balance in the blink of an eye. Here's our process flow diagram. Right, we'll not assume that the feed is equal to 1, but in general we do. Right, we have the composition of A times by the feed. This is the total amount coming in, leaving the system. Right, and the feed. Voila, right? Mass balances, no hesitation. In equals out. Our consistency relationships. Okay. Summation of the x's have to equal 1. And lastly, our 2 Raoult's law expressions. Done. Yes?
What was it again that you called the summation of the fractions?
Consistency relationships.
That's what I was thinking.
Basically, they're just definitions. That has to be true based on how we define what a mole fraction is. Because a mole fraction innately is just a definition, right? We're defining what a mole fraction is. Okay, so in this example, we are looking to solve for YA, YB, XA, XB, L, and V. We know the system temperature, we know the system pressure, we know what component B is, so this vapor pressure is a material property that we can look up. Same thing for A, same thing for B. So, 6 equations, 6 unknowns, figure it out. Right, that's essentially what a flash calculation is. Now, we'll go through some strategies, but in general, this is something you need to be ultra familiar with when it comes to exam 2 time. Right? A flash calculation needs to be innate and just sort of automatic. So all we're doing is substituting stuff into stuff into stuff into stuff and then making it all work out. If you want, you could build a giant matrix and solve this all with linear algebra. Totally fine. Right? As long as you're consistent, it should all work out. So we'll be doing this more and more as time goes on, but right now I want to simplify these equations for the bubble curve and the dew curve. Because these 6 equations are the 6 equations that are exactly the same ones used for the bubble curve and the dew curve. And this always throws students off. Right? It's based on this approximation is what allows us to generate the dew and the bubble curve. Right? This is the key to the dew and the bubble curve. This is the same always. This is always true. All of these equations are never invalid for a 2-component system. But how we approximate them to get the bubble and the dew curve, that's how we generate those lines in the TXY and PXY diagram. Okay, so let's start off with the bubble curve. What is the bubble curve? Can someone describe it to me in physical terms? What is happening in a PXY diagram at the bubble point?
That's when we see the first bubble.
But how do we get the first bubble? Yes?
Is that when the more volatile substance first starts to become vapor because the other one won't vaporize at the same pressure?
In a sense, yes. The more volatile component will actually drag with it some of the less volatile component.
Okay.
So what the bubble that forms will have a little bit of everything in it, actually. How do I
I was just going to say we're depressurizing it.
Yes. What are we depressurizing, though?
The system.
Well, we don't know what the pressure is, but we're depressurizing a 100% liquid mixture. We know that we have 100% liquid. And we know, if we know the total composition, look up here, Xi equals Zi. If we know the total composition, that means we know the liquid composition. What don't we know anything about? The vapor. Which of these 6 equations focuses on only the vapor phase?
This is the one equals XA.
This one right here. So we're going to start with this equation. Why? Because as soon as we can substitute out a term for every one of these unknowns, then we've solved our system and we can actually calculate something, right? So we're going to start off with the most difficult equation we can, the one that focuses 100% exclusively on the vapor phase, because we are 100% liquid and we are forming that first vapor phase. Okay, so our starting point is going to be 1 is equal to y of A plus y of B. Now, next, which of these equations relates between the liquid phase and the vapor phase?
The top one.
This one does, but I'm also kind of throwing a wrench into things. If I use these top equations, I also have to solve for L, and I actually have to solve for V. So which one should I decide to try?
The Raoult's law.
Raoult's law. Can I rearrange Raoult's law to solve for our unknowns and our starting point? Right? Trivially. It's just y of generally species I is equal to x of I times by its vapor pressure divided by the total system pressure. I substitute this expression into here, and I'm going to write this generally, summation of xi pi set times by t over the system pressure. And I'm almost done. Okay, do I know my x of i's? because I know my total composition, because Z is equal to X. Right? The total composition is equal to my liquid composition. Do I know my saturation pressures? Right, we should be able to look them up. Do I know my system pressure? No, we're trying to solve for the bubble curve. Right, we're trying to solve for that. So I rearrange this. P, we know this is equal to the bubble pressure because of the assumptions that we made here. But this equation is totally valid for a flash calculation, not at the bubble point. What makes it the bubble point is this approximation where X is equal to Z. Right? But you're doing that in your head. Right? Because when you're given a total composition, you can solve for both the dew point and the bubble point, right, with that same Z. But sometimes it's X and sometimes it's Y. That's the confusing part. The bubble curve is equal to the summation this is your bubble curve equation. So on the Pxy diagram, this is a straight line. Right? Because if we rewrite this for a two-component system, it's going to be X of A times PA star plus 1 minus the mole fraction of A times by the vapor pressure of B. This is the equation for a line. It is a linear expression. And that's why we get a straight line for the bubble curve. Yes?
So the xi is equal to zi.
Correct. So for a 50-50 mixture here, right? For this line that I've drawn, if I take an all vapor system, let me pull it down here. If I take an all vapor system and I pressurize it, I solve for the dew curve. If I take an all liquid system and I depressurize it, I solve for the bubble curve. Right? So that same total composition can be used to solve for both the dew and the bubble curve at the same time. Yes?
Sorry, just to follow up on that. So would you, I mean, you might be getting this, but to get the whole curve, would you vary xi? Like, does it matter?
Yes.
Okay.
Yes. So the bubble curve is a collection of all the bubble points. So what you would do is you would go from XA equals 0 to XA equals 1, and you would repeat this calculation for every single point. And then you've generated the bubble curve. So essentially, the bubble and dew curves are every flash calculation that could ever be calculated. Does that make sense? Now, the Txy diagram is exactly the same equation. Except in the Txy diagram, you know the system pressure, but you don't know the temperature. So in the Txy system, you have to solve for the temperature such that this equation is satisfied and equals the system pressure. So for the bubble, for the Pxy, you have explicit equations. For the Txy, you have implicit equations where you have to use a nonlinear solver. But this equation is exactly the same. So for this week's homework, you'll be generating Pxy diagrams, not Txys. Next week, it's a Txy, which means that in a Txy diagram, every single point at every different z value is a nonlinear equation you have to solve. Right? So generating a Txy diagram involves solving like 40 or 50 nonlinear equations. But it's the same functional form, so you can automate it. It's not that bad.
So you just run a loop then?
Yeah, you can run a loop, or actually Excel solver it knows that the equations aren't dependent, and you can solve them all in one go and solver too. Or you can do a loop in MATLAB as well. Okay. Now the dew curve, we are going to do exactly the same thing, but just opposite. So in the dew situation, we know everything that we need to know about the vapor phase, right? Because we're assuming that there is a teeny amount of a bubble, of a liquid droplet that just starts to form. So in the dew curve, or rather the dew point, right, we have all vapor and we're trying to figure out what is going on with the liquid. So let's start off with the hardest part. 1 equals x of A plus x of B. Now we just need to substitute in expressions for x of A and x of B, the mole fraction, and let's use Raoult's law again. Right, so in that case, I'll write it generally. The mole fraction of species I is equal to the same fraction in the vapor phase times by the system pressure divided by its vapor pressure.
Wouldn't it be flipped? Pi star be on top?
No, so all I'm doing is I'm dividing both sides of the equation by the vapor pressure.
Oh, okay. Got it.
So then I can rewrite this more generally, right, as the summation of the mole fraction in the vapor times by the system pressure divided by the saturation pressure. Now I just need to solve for P. So 1 over the pressure, which is going to equal to 1 over the dew pressure, is going to be equal to here, but more generally we rewrite this so that it says P dew is equal to 1 over and this is clearly a nonlinear expression, right? You have your variable that you're plotting here in your denominator, right? So it's kind of like a sort of a radical shape. And you can see here that on the dew curve, it does have sort of that sort of radical shape you would expect, kind of curving up like that. So in order to plot out a Pxy diagram for the bubble curve and the dew curve, you have to apply this expression here, where you vary the composition of your system, going from maybe 0.01 to 0.99 in whatever point increments seems appropriate for the resolution of the graph that you want to make. You put in XA, and you solve for the pressure. Here, you put in Y of A, and then you solve for the pressure. You plot your X, your P versus X, because Z is equal to X in the bubble curve, right? And then in the dew curve, you plot P versus Y, which is equal to Z. And you should get something that looks like this. Now, if you want to generate a TXY bubble and dew curve, it's the exact same equations. But you have to solve for the temperature such that the dew pressure equation each equals the system pressure that the TXY diagram is drawn at. So it's a system of nonlinear equations. They're not connected, right? They're all independent, but you have to solve the same nonlinear equation again and again and again. So in question, I think 7, it's 6 or 7 on the homework, I don't remember which one. But you have a 3-component system where you're solving for the dew point and the bubble point, right? And that's where we use these generalized expressions here. Right? So instead of just having A and B, it's A, B, and C. But you know the A, B, and C. It's a third, a third, a third in that particular problem. So the key thing then is to finishing out this calculation is that once you know the bubble curve and the dew curve, right, all of the other equations are valid. So if I want to know what my composition is of the liquid at the dew point, I just use Raoult's law. Right? Because if I know what my Y composition is, because it's equal to my Z composition is, then I just have to plug all that information into Raoult's law, and I solve for what my liquid composition is. Does that make sense? Because you'll need to do that on question 6, I think, with a 3-component system.
Is this the plot? Sorry.
Was that?
Is this the plot?
No, the plot one only relies on you knowing how to read the Pxy diagram, but I think question 6 depends on knowing how to apply Raoult's law after the bubble point calculation, right? So what you need to do is you need to first solve for what the bubble point or the dew point is, then you know the pressure, then you know the composition of one of the 2 phases. Then you can plug that information into one of Raoult's law's expressions to calculate the composition of the other phase. Does that make sense? Are we guys reconnecting the dots? So We know z. From z, we know y, if this is the dew curve calculation. From y, we can calculate the p using the dew point calculation. From the p, we can calculate the x using Route's law. Right? So this right here is the dew assumption. This one here is the dew point. And this one here is Route's law. And then we can know both the y and the x composition. But this is only valid at the dew curve, or we do it the opposite way, it's valid for the bubble curve. Now, if you're not at the dew point and if you're not at the bubble point, you have to use the full 6 equations, 6 unknowns to balance the whole process out. Right? What we've talked about now is only for when our system composition and our system pressure meet at either the dew curve or meet at the bubble curve. If we are somewhere in between the two-phase region, right, then we cannot know anything about what x's are and what y's are. The only way we know what x's and y's are for the dew and the bubble curve is because of the assumption that we made here. If these two assumptions aren't valid, we have to do the full form of the flash calculation with 6 equations, 6 unknowns. Right? But we can use the simplified version to generate these curves here. So if I can solve for the dew pressure, I can solve for the composition of the liquid phase at the dew point using Route's law. If I know the bubble pressure, I can solve for the composition of the vapor phase at the bubble point using these approximate and simplified equations. But if I am anywhere in between in the two-phase region, I got to use the full form of everything here with 6 equations, 6 unknowns. There's no flash calculation on this week's homework, but there's a flash calculation on next week's homework. Questions? Hopefully this all made sense. But if you're familiar with how to read the Pxy and Txy diagrams, hopefully this should seem a little less daunting of a task. Question? Okay. Have a great weekend. See ya.